So in this talk, I'm going to introduce you to the work that NIST is undertaking for standardization of MR methods, and we'll talk about some of the tools that are available that you all could start and have started using. So generally, standardization isn't super exciting. And I've been at NIST for almost 10 years. So I think it's fair to ask, like, why am I still here and doing this? So what gets me excited about this work is the possibilities of diagnostic quantitative MR. And so I like to think about a time in the future that we are getting closer to, where quantitative MR is going to be more perhaps like a blood test. And so you would have the range of the quantitative MR parameter, and you would know what the patient's result is, where that falls. You know, we have these maps with T1, say, we know what the value is. This amount of information, though, right now is not useful. We still need to know what normal is in order to make a diagnostic statement about the patient's value. And then the other aspect that's missing here is the uncertainty. And how large is that uncertainty? How confident can you be when you make these statements? And what we're working on at NIST and engaging with others to do is to work on, reducing this uncertainty. And then also understand, if we want to look at these different quantitative MR parameters, what certainty do we need in order to threshold a disease state? So one place, I'm excited because we've seen all these different quantitative maps today. There was this nice review paper that came out last year, Granciera et al., looking at many of these techniques in the brain. And so they looked, you can see at, T1, at magnetization transfer, diffusion, T2, and looked not only just at, where you would use it. In this case, they were considering, normal pathology or evaluating MS lesions. They also looked at how reproducible and how available, which is an aspect we've been talking about today with the availability of the different MR scanners. So how reproducible and available is it? And I was really excited to see this work because it considered these two aspects that are pretty important. We are at a place where reproducibility and uncertainty and availability are preventing us from using these techniques on a regular basis. So NIST started a program in quantitative MRI about 15 years ago. And the first step was the development of these reference objects. And these were developed in collaboration with folks at NIH, different professional groups that we're familiar with, like ISMRM, RSNA-Kiva. And then right now we're at the stage of really getting these out and used by the community. Other changes that have happened over the last 15 years is that NIST isn't the only, NIST is a National Metrology Institute, and we're not the only one working in this area anymore. So it's exciting because there's a real community building up to do this work. So my colleagues, Stephen Russick and Carl Stupik, work on our primary NMR calibrations. So you can see there a diagram of our NMR system, and being NIST, we make sure that the clock on the NMR system can be traced back to the primary time standard. And we do that for other measurements that are important. And then the goal is that we well characterize these solutions that go into the phantoms, or at NIST, they're reference objects or calibration structures. And our goal then is that when you're making a quantitative map, we've seen fingerprinting maps today, you would have these in vivo measurements would have a bias. So how far off is my scanner's measurement? And an uncertainty. What's the error in my measurement? So these objects have been available for use for this one in particular for about a decade. And so one study that we did was we sent the object across the United States to look at the variation in different MR systems. And so we asked sites to make the same measurement of inversion recovery and variable flip angle for T1. So they were using as close to the same protocol as we could implement across different vendor systems. And that allowed us to isolate the variability of the system rather than the technique. And all the data was analyzed by NIST. And that, again, removed some variability in the model selection. And so what I'll show here is the results from that study. And so the y-axis is our deviation from the NMR or the NIST known value. And the x-axis is the different T1 relaxation times in the phantom. So we looked at approximately 24 systems from 3 different vendors. And all of this data is at 3 Tesla. And so you can see here that for inversion recovery, as expected, it's long and slow. We're making a high quality measurement. There's not much bias. There is an appreciable difference at these last few T1s for this particular vendor. But on the whole, we're pretty happy. Things got more interesting when we looked at variable flip angle measurements. So here, the y-axis scale has increased. We have a lot more deviation across the vendors. I should say that this data was actually collected quite a few years ago before B1 mapping was available as widely. And so there's no B1 correction here. So that'll decrease the error and remove some, this pattern here will go away when you do a correction for B1, we expect. But so we do see these differences between the vendors, especially when we consider, normal T1 values of tissues that you heard everyone discuss today. So this is a little discouraging, but we, by knowing it, we know more. So how do multi-parametric sequences perform? Cowan had talked a lot about different multi-parametric sequences. Others have shown results. So in this study, there was definitely bias when comparing the different scanners. So the different lines here are different scanners. And one thing that was encouraging was there was less variation when they looked in vivo than when they used the phantom. Another, when we first started doing this, a totally fair question we get a lot was just, well, who cares about your phantoms? Like, what about in vivo? Because that's what we're really looking at. And so there are these 2 papers that showed that there was really minimal differences across systems in vivo. I want to just call out a clarification here, or a point, that the study on the left was the same hardware, the same software, and the same sequence. So that's something that you can do right now at 0.55T and even at 7T. But that does get challenging if you want to, you might not have as nice a result as you look to different vendor systems. And the study on the right, it was different hardware and software, but they actually customized the sequences line by line to get the same implementation. So that's a lot of, it's pretty intensive work to get the same result. Here, Lee et al. Was looking at white matter T1. So here we have the T1 value, a histogram of values in 7 different participants. And this is, again, for white matter. And there were 2 different vendor systems. So the solid line is one vendor, and all the dotted lines, the dashed lines, are another vendor. And it's obvious here that there is a bias in vivo when we're working across different vendor systems. So we need to be aware and take caution. There is this bias that exists, and we've established it in phantoms, and it's been established in participants. We also should think about system upgrades. It's everybody's favorite, I know, for software and hardware upgrades. So in this paper by Lee, they actually had a system that underwent an upgrade. And so the dashed line is the pre-upgrade, and the solid is the post-upgrade measurement. And again, we see that there's a change with the upgrade. In this case, it was a software upgrade. Our group studied a system that had both hardware and software upgrades, and we also saw a bias in the measurement post-upgrade. So you should all be aware that your MRI system is not stable over time. So we have some challenges, right, in reproducibility, uncertainty, and we really need to look at making quality assurance measurements. So those measurements can help you identify the bias, know that it's there, and track any changes in your system over time. So we would suggest that you find an appropriate phantom or reference object. These are being used more for single time point measurements, to qualify you to participate in a study, say. But based on the changes that come with an upgrade, we really suggest that you use it more frequently than just a single time point. So what phantoms are available, and I'm happy to discuss offline with anybody what might be appropriate for the work that they want to do. But the number of high quality stable phantoms has really expanded over the last decade. So the ADNI phantom and the FBurn phantom were early stable phantoms. And then in addition to the NIST developed phantoms, there's now a commercial version of the PDFF phantom that was developed at University of Wisconsin. Groups at Berkeley and Martino Center have put out different anthropomorphic objects, which are really neat. And then Walt Schneider is leading an effort to include components for DTI in a phantom. I will say for the 7T crowd that I don't think there's anything that's great for a microstructure phantom right now. That's an area that's pretty challenging. And whatever you do when you think about the phantom, I want you to really look for something that's stable, and it should be physiologically relevant to the study that you want to do, because you want to perform the same sequences, excuse me, in the same protocol that you would when you're doing your in vivo study. So at NIST, we are thinking about other field strengths. We started at 1.5 and 3T for obvious reasons. And a postdoc on our team, Kalina Jordanova, is examining how we could develop a phantom that might be useful across field strengths. But it's pretty challenging. You can see here, so these are different values from the literature of the T1 in white matter and gray matter across field strengths. And there is no obvious material candidate that replicates tissue in this way. And so just to highlight the fields that are the focus today, and just how they differ from 1.5 and 3T. So I did mention that NIST is looking at this, and one thing that's great is recently, over the last few years, we've really improved our ability to make measurements across fields. So we are reviving, you can see this system here is not new, but we're reviving an old electromagnet that would enable us to make measurements at 0.55T. I was just talking to a colleague who's doing some plumbing on it today. And then we've had an NMR system that we can ramp to 7T, but we're actually in the process of purchasing a cryogen-free field rampable system from Superconducting Systems. And this will cover both 0.5 and 7 Tesla. And what an advantage here is that we can take the same sample leave it in place, and then change the field and make our T1 and T2 measurements and diffusion measurements. So Michelle Martin is a postdoc in our group who's been using that electromagnet and other low field systems. And so she shared just some preliminary measurements of the system phantom materials. So there's nickel chloride and manganese chloride in the phantom. And so she is, in the process of trying to support those of you who are working outside of 1.5 and 3T. And there is, there is literature looking at nickel as a material, nickel chloride as a material. And so encouragingly, the results that Michelle's getting agree wherein, there's no variation, there's no dispersion with the field strength change up to about 3 Tesla. We do know, though, when we look back to the work that Keenan has done to gather all the measurements from the literature, that when we, so here I've added the gray matter and white matter expected values for 0.55 T to these plots from Michelle. And so different solutions in the phantom are going to be physiologically relevant. And one thing that we need to be aware of that you can see here is that there might not be distinction between the two tissues based on the solution in the phantom. And so I guess it's encouraging for all the work that's been being done outside of the brain, because we have many more solutions that should be relevant. We worked with folks at DISC with Ye and Jibo to make preliminary measurements using the system phantom. And so here we have a gold standard T1 measurement and a T2 measurement, and then the turbo spin echo T2 and MRF, and here a B1 corrected variable flip angle and MRF, along with on this T1 plot, NIST's preliminary measurements. So you can see where the tool is going to be useful to help us understand the measurement method and the accuracy of what's going on. And you can see that there's still some things we need to better understand about these measurements. We have also done work with Yifan Yen at the Martino Center looking at 7 Tesla measurements. And so here we took a modified phantom based on the coil size that was available. And Yifan did T1 mapping to look at repeatability. And it was some of the first 7T data that we have of the system phantom. And so on that system, there was excellent day-to-day repeatability. She also used the system for comparison of the coils that were available. And so this is an example of how you can and maybe should use these tools that are available to you to validate your measurement methods and assess repeatability. And so just, I called this the super plot, but I added here some preliminary 7T measurements in addition to the data at 0.55 T. And so the good news is that at NIST, we are working to make, our reference objects, our phantoms that are available, useful across the field strengths. And hopefully over the course of the next year, once we have our new NMR system, that becomes more readily available. So as you all are developing new techniques and improving measurement methods, possibly discovering new biomarkers, I'd encourage you to think about the standardization and how you assess the reproducibility, how we make the measurements the same across sites, because that aspect of it is really key to enabling us to advance quantitative MRI as a diagnostic tool. So I want to thank everyone at NIST and my collaborators elsewhere who contributed to the presentation. And thank you all for your attention.